Okay, yeah, good morning, everybody. Welcome to the first distinguished lecture series of the Future Lab. And today we have the pleasure to have Professor Pavan Angelov to give us a talk on explainable AI. Pavan and myself, we are connected through Alice collaboration. And we figured out there are actually quite some common interest between the two labs. Therefore, we want to have a more in-depth exchange. Thanks a lot, Pavan, for taking your time and give talk here. And in particular, I heard that you are on leave. Yeah, so before you start, I would like to read a few points from your biography. Then everybody get a little bit more about your background. Professor Angelov is a fellow of the IEEE, of the IET, and also of the HEA. And he is basically having a lot of community roles. And particularly, he's holding a personal chair in intelligent system at Manchester University, UK. And he has authored more than 350 peer-reviewed publications in leading journals. And it's a very well-cited researcher. And the point of why we get connected is because of the common interest on explainable AI. But he is actually also a founding director of the Manchester Intelligent Robotic and Autonomous System Research Center, which includes over 50 academics across 15 departments from all faculties of the university. And I think he definitely has a lot to tell. And now, without further ado, I will hand over to Pavan. The floor is yours.
Okay, thank you. Thank you very much for this opportunity. Thank you for the introduction. And I'll start my talk, which I entitled Interpretable Deep Learning from Earth Observation Data. However, I want to clarify that in the title, Earth Observation Data came towards the end. We just started a new project very recently. It's second month, maybe. I'm on leave, actually. So there will be an example and a little bit on that, but the talk will be in three groups. So I'll talk about the center in which I'm working, which I founded and I'm director of, LIRA, and I'll talk about explainable and interpretable deep learning and some applications, including Earth observation data. So this is the plan. And let me start. So first I'll talk about LIRA, or Lancaster Intelligent Robotic and Autonomous Systems Center. And then I'll talk about interpretable deep learning. And I want to give credit to my PhD students, Eduardo Suarez, who is submitting now and finishing in a month or so, and Xiaowei Gu, who already is a lecturer in another university. But the work started with them and with some other PhD students before them, like Dmitry Kangin and so on. Also, Professor José Principe from University of Florida was involved in the development of theoretical aspects. I'll not have much time, as I was informed, so even this topic I'll cover just with some concepts and principles, and I'll not go into too much detail. I'll point towards some of the publications, and if there is an opportunity for a longer talk or another chance, or if questions arise, I can cover more details. So I will talk mostly about motivation, context, challenges, and in a nutshell, the proposed approach. Then I'll move to applications, which will form essentially the second part of the part two, which may be of more interest, and I'll try to focus on remote sensing, which is related and observation that we just started with the project that is part funded by European Space Agency, and it's FieldUp. And I'm listing here, I give credit to the PhD student who just started, Jiang Zhang. In fact, will be co-supervising within the framework of ALICE with Professor Zhu, and also Eduardo Suarez, with whom actually we put the proposal, and a couple of people from ESA, European Space Agency, Nicolas Wongep, and the director of the FieldUp, Pierre-Philippe Mathieu. So let's move to LIRA Center. It's if you want research center in some respect like administrative organization, but it's not vertical, it's horizontal structure. Vertical structures are mostly for management, like faculties, departments, but our university has also a number of institutes and centers, research centers, which form a horizontal structure, which is mostly based on research interests, much less on teaching and other activities that go on in the university. And they're definitely interdisciplinary and collaborative. And one of such centers is LIRA, which was established, co-founding director, a few years ago, 2018, in response to the surge of interest to artificial intelligence, autonomous systems, and robotic systems. And some of the national documents in UK, their logos are pointed underneath, but you are probably well aware that there are such activities in practically all developed countries, in EU, and so on, related to these topics. So LIRA epitomizes and facilitates the transdisciplinary and collaborative work. We form networks, we have workshops, we issue newsletters, seminar series, joint projects, and in fact, some of your colleagues probably will be soon invited to give talks as well in return. So these are probably well-known activities of such horizontal organizations like this center. And also we establish or try to get big projects together in a collaborative manner. And also very often we are consulted by, like in UK, this is House of Lords or the government even on some advisory issues. So it's a focal point of interest towards intelligent, autonomous, and robotic systems, and also the related machine learning and AI. So LIRA brings together at the moment 60 faculty or academic members. In addition to that, there are a larger number of PhD students, and this comes from most of the departments of the university, more than half of the departments. And we have a number of fellows of IEEE, ACM, ALICE, distinguished professors, and this is the building where InfoUp is based. There are 8 sub-teams or groups, if you want, within LIRA, and they cover the fundamentals or theoretical aspects, also number of application areas of interest. Nuclear and decommissioning, because in the northwest of England, there are, even near Lancaster, there is a nuclear station, but there is also decommissioning plant Sellafield, and there is a lot of robotics and autonomous systems applications related to these problems. Also advanced manufacturing, Industry 4.0, security, defense applications, intelligent transport is an increasingly important topic, like driverless cars, environment, and advanced agriculture related to linked with UAVs and image processing and so on. Biomedical applications is a very big topic as well, and also social and human applications. We are an organization member of the CLARE network. Also, we are currently applying for the ALICE unit to be a officially recognized ALICE unit, but we are already part of the ELISE project, which is actually the funded project run by ALICE. We are also part of the Taylor project, which is run by CLARE. Also, we are initiated and chair the first standard on explainable AI within IEEE. I was actually a chair in 2010-11 of the standards committee of IEEE Computational Intelligence Society. So this is already ongoing activity. As you probably know, each standard is a long process which takes 5 years or so. So we initiated, and it's in its first year. So there is such a standard activity. We're also very active in another organization called International Neural Network Society. So we are actually part of larger networks and ecosystems, if you want, of international organizations. Related to projects and our research strength, this is just one poster from one of our projects for over 1 million, 1.3 million, I think, pounds, recently finished, which developed a prototype, physical prototype, which is here actually represented for an underwater robot which is crawling. It's not swimming, but crawling to clean the waste, nuclear waste in this cell field plant, as I said. So there were a number of challenges. It's like amphibious vehicle, if you want, with a cable. So it's fully autonomous. It's not remotely operated. And the vision was challenging because it's based on point cloud and so on. So there are a number of interesting research challenges that we addressed. There are a number of other projects. This is just one example. Currently, we are running another very big project on trustworthy autonomous systems and their security. So we cover topics like explainable deep learning, remote sensing, autonomous driving, medical images, and so on. So I'll try to show some examples in the second part of the talk. Here are logos of some of the projects that we are part of. I mentioned Elise and Taylor, and European Space Agency, which is funding this project. This trustworthy autonomous systems task security is the logo is here. We have also grants from National Center for Nuclear Robotics, Ford, meaning their research and innovation base in Palo Alto rather than the traditional manufacturing of cars. So we are not dealing with cars per se as a powertrain, but with the advanced driverless aspects, image processing, and decision-making, recognition, and so on. So also we have funded projects from Defense Scientific Technology Lab, DSTL, and a number of other research councils, which are pointed here. We gave a number of talks at conferences and number of awards, and we also, including in Silicon Valley, in Facebook, in developed organized workshops at NeurIPS, ICML, and so on. And a number of publications were published in leading journals like PAMI or IEEE Transactional Cybernetics, and so on. And I mentioned that our members were asked to consult the Cabinet Office, which in UK it's actually the government, like Chancellery in Germany. As infrastructure, this is the building from another angle. We have our own space, lab space, which is not huge. We are discussing to enlarge it actually because we have some hardware, robots, and autonomous airborne UAVs or drones, as they are known more popularly. We have administrator and small annual budget, mostly to support seminar series and visitors. And we run newsletter, seminar series, as I mentioned, and so on. So this is about the center. I was asked at the beginning to give more information about the center, and this is my first part. Now I'll start the more scientific aspects, if you want, my talk. And as I said, it will be broken into two parts. The first part, I will present the theoretical foundations, but in a nutshell, because the time is short, and then some applications. So talking about explainable and interpretable AI in general, it's a little bit strange, if you want. I feel a little bit strange or funny, because AI, by its inception, if you want, in the middle of 20th century, developed a number of approaches which are clearly explainable and interpretable. So starting with decision trees or rule-based systems and so on. The problem actually appeared in the last couple of years, mostly related to the more advanced machine learning forms, in particular deep learning, because there are explainable AI. So when we say explainable AI, it's a little bit of a nonsense, because there are explainable AI approaches, but they're not so efficient, let's say. While there are very efficient approaches developed very recently or excelled very recently, they were actually developed earlier, but on another basis, let's say neural networks, for example. They, in particular, need such attention, or they lack this interpretability or explainability. So when we talk about interpretable, we should talk about interpretable deep learning rather than explainable AI, I think. So deep learning offers high accuracy. I mean, this is to some extent you'll find trivial, this slide, because everybody knows now this, but let me start from there. So deep learning offers high accuracy and achieved a lot of impressive results, often surpassing human accuracy, if you want, can increase tremendously the throughput and efficiency of many operations, including decision-making, pattern recognition, and so on. However, it has its own, it comes at a price. It has its own shortcomings, if you want, and we need to be aware of that, and we need to try to address them. This includes its opaque or cumbersome nature. This was well known in the 90s when neural networks were in their first boom, if you want. They, as you know, they were invented even much earlier in the middle of the 20th century, but around 90s when I was a PhD student, and actually I started with this, or even 80s, they also had a boom, neural networks, and people criticized even at that time, but it wasn't so huge problem because the number of coefficients, weights, and so on was not so huge. Now there are deep neural networks with not only hundreds of millions, but even billions of weights or parameters. And what is worse is these parameters are not directly related to the physicality or the nature of the problem. So they're abstract parameters, they're numerical parameters. So how you are going to explain this to a user, medical, driver, or any person with the normal skills? So there are tens of layers which are also to some extent ad hoc. They are selected by the designer of the problem, not necessarily related to the problem itself, and so on. So also the same problem actually leads to the fact that it requires a lot of training data, huge amount of training data, and a lot of time very often, which can be shortened if one is using hardware accelerators like graphic processing units, GPUs, or high performance computing. But also it's very often prone to overfitting. It requires high energy, a lot of energy because of that, and related to space applications, also weight related to this specific hardware and so on. So there are a number of issues that can be improved or challenges which lead to the desire to develop more efficient, if you want, architectures and methods even. And I'll try to talk about this. So when there is also new data pattern, change of the data pattern, retraining is required as well. So they are not flexible and adaptive. They don't evolve. You don't have an evolving structure. Like in some models, you can have like linear, especially. You can have adaptive linear systems or some relatively simple nonlinear as well. And what is also even worse is in some maybe relatively rare cases, like it was with the Uber car in 2018, they can give a completely wrong answer with high confidence and without explanation even why. So even if after the fatal incident, we accept it as a fact, we would like to see why and to analyze and to learn from it. And it's not possible or not easy in any way because of this cumbersome structure. So there are a number of challenges. And one of the reasons we came to this situation is the data-rich environments that we live in now. Nowadays, we live in environments where huge amounts of data are produced on a daily basis, on hourly basis. You know, we carry on gigabytes in our pockets, literally with mobile phones and USB flash disks and so on. Terabytes of data per day, and it's growing exponentially. So in my view, we can talk about Moore's law now, but in regards to data rather than to hardware as it was in the 20th century. The data is of different nature as well. There are streaming data, so you have time dimension. There are heterogeneous data, not just images, but natural language processing, as well as other regular physical data and so on, irregular sampling. And this led to the temptation to shortcut from the data directly to the solutions, bypassing the not only causality, but the deep insight understanding of the problem. So if we sketch in a very simplistic terms, explainability and accuracy, there are a number of methods, as I mentioned, which are already explainable, like rule-based decision trees, but they are not as accurate as deep neural networks, for example, or even simple KNNs, which are not strictly speaking machine learning. So the ideal, or let's say the holy grail, is to develop some method which is in the upper half of this, upper right half of this graph here, or this plot, which will be as explainable or even more than the existing other methods, but also as accurate as possible. So this is what will try to address. So let me show in a nutshell our approach, which is essentially a prototype based. So number of challenges exist, and I'll show directly to which solution we tend to or we prefer. So the first question is, do we need really highly parametric models with billions of parameters which are fully abstract and not related to the problem? In the middle of this spectrum is the physical models, which have a small number of parameters and they're directly related to the physicality, but they have their limitations and so on. And in some applications, they are still being used. But on another extreme of this spectrum is the prototype-based models, which may not need even any user or artificial parameters, let's say tunable parameters. All of their parameters may be extracted entirely from the data. And this is what we prefer in our approach. Also, the question of functional or symbolic, because symbolic AI was probably even the first approach, and now some authors call it old-fashioned AI and so on, but it has its own disadvantages. So do we combine, or do we look at the symbolic as well? Local or general or global generalization. Generalization is very important, but do we need a global generalization, or local generalization is preferable? And our approach that I'll describe, we call it explainable deep neural networks, or explainable by design if you want, is based very much on this following Cauchy representation, which, as I mentioned, I don't have much time to come to describe how we came to it, but in other talks I'm coming to this step by step. So let's assume that this is a fair representation of the density of the data, which is akin, or not exactly, but is very much related to the PDF, or let's say it's related to a empirical PDF if you want. And it's not a Gaussian, but it's close to Gaussian, and it has very interesting properties. And if you notice, there are no any user-defined parameters. The only parameters are the mean of the data, which comes from the data mu. Mu is mean here. And also X is the data itself. So apart from the data itself, you don't need anything to develop such representations. And also it can be recursively updated, unlike exponential, a Gaussian exponential. For example, if you have another new observation, so you had already, let's say, 1,000 observations, and you have 1,001st, you just update it recursively, which is very important for streaming data, for computational efficiency, and so on. Okay, so based on this notion of density, which in fact is very similar also to what in fuzzy logic they call a membership function, because it's not PDF actually. The maximum is 1 here, as you can see, and it's between 0 and 1. But using this notion of density and making a weighted sum, one can derive the empirical form of conditional probability. As I mentioned again, we derive this step by step, and it's quite logical. But in this talk, I just shortcut it and got the results. So the conditional probability for membership to a class can be expressed as a weighted sum, if you want, of these densities. And then we have a very powerful representation of either continuous in this form with the integrals, or the discrete form in practice of the distribution of the data, if you want, of the density, or empirical PDF estimation of the PDF. So I have a book which describes in much detail, and number of papers which I can point to, and I can talk, but I will need a couple of hours to derive it step by step. But you can see the results here for climate data, for example. If we compare the conditional probability, or what we call it typicality, this expression, in fact, the discrete one on the right, we get the red bars here, the red lines. And if you compare with the histogram, the pattern is there. It's slightly different, very close approximation to the histogram. If we compare with the traditional approach, when we derive just one Gaussian exponential, the green line, you can see it's far away. If we know that there are a mixture of two Gaussians, for example, we can get a better approximation. But in many problems, we don't know this number, because these are simple data. These are real data for the climate near Manchester. in UK over 3 years period, but with the climate, it's relatively simple. With other data, it may be highly multimodal. You may have too many peaks like here. So essentially, what I want to say is that we developed a method where you can directly calculate from the data without any parameters an estimation of the PDF. Of course, it's discrete because your data is discrete. You have a finite number of data, so you will get not exactly what is on the right, but a discrete approximation of it. And then you can make an envelope, meaning a local approximation, not global. But the most important information is the peaks, local peaks. So you would have this, you can have this information about these peaks quite precisely, quite accurately. And the approximations will be only locally. So when you derive this directly, it's very fast and computationally efficient. This is what we call empirical approach to PDF. Here is the envelope. We focus our attention on the peaks only. We are not so much interested in the rest. We are focused on the peaks, which we consider as prototypes, local prototypes to describe the properties of our data. Of course, in general case, there are many dimensionalities, many features, if you want, or parameters, variables. In this 3D plot, we use principal component 1 and 2 just to visualize. And then you can develop any classification approach because you have the typicality in a closed form. So it's like generative approach. Here I visualize, and this is part of one of our papers in IEEE transactions, additional material. You can see this video as well. The process, the way it develops step by step. One big advantage is that it's recursive and it's evolving. Evolving, it means that the more data are provided, the number of these local peaks and their location and position may change. We don't need to predefine. So we don't know beforehand, are we going to use a mixture of 10 Cauchy functions? We don't use Gaussian, but Cauchy kernel, or how many? It derives and is driven entirely by the data without any user-defined parameter. And it depends on the data. Or roughly speaking, if all the data are homogeneous and drawn from a single or two Gaussian distributions, we should just derive two peaks, experimentally approximate them. But because usually data have many more local, so like in this case, temperature and wind, it will mean hot on the right, and on the top will be windy. In the bottom, it will be hot and without a wind day. On the left, it will be cold and without a wind, and so on. In the middle, it's windy day. So they carry on meaning as well. So it's derived from the data entirely. Of course, if we carry on this process only once, the way I described, without any parameters, we'll get too many local peaks. Therefore, we developed an approach, staged approach, where we apply this first, then we get these local peaks, the black dots, then we ignore all the actual points, original points, and we repeat the process, and then we get smaller number, and then again and again. In this way, we get several embedded, if you want, levels of aggregation. So in this way, we developed our internal architecture, if you want. Based on this, we have several layers of aggregation of the prototypes. So based on this, we developed our architecture of a deep network, if you want, which also has linguistic representation. I mentioned about symbolic, so we can have a if-then rules as well. And let's assume we have an image processing problem. We developed an approach to train per class. So it's different to the traditional approach where training is all classes together. We develop per class within the class, it's like unsupervised. So it's more like clustering or segmentation, if you want. An approach where we extract features from the image, then we calculate this density that I mentioned and typicality, or this empirical PDF, and based on them we select the prototypes. But the first layer is all the prototypes. There are too many. Then we have more aggregated prototypes and so on. And at the final layer we have the top level prototypes, which are smaller number, but they combine a lot of information. So we have similar architecture, if you want, to a deep network, but derived in a logical manner. So it carry on the meaning of the problem, but also it does not have this billion of parameters. Then we make a local decision per class, which is based on the winner take all principle. And then we make the global decision, which is across all the classes. And finally, we declare the winning class. As a feature extractor, we can use any approach if it's in an image processing, GIST, HOC, histogram gradients, or so on. Or we can also use a pre-trained deep network as well, optionally, but it's not a requirement. Of course, if it's not image processing, this technique also applies. Then in many cases, you do have the features directly, like velocity, pressure, temperature, whatever, they are known. But in image processing, they are not clearly known, the features. So this is a description of what each of these layers actually do. I'll just skip this for the sake of time to show you more applications. And we started with different image processing problems. I didn't include it in this talk, I believe all of them, but the architecture for training is different from the architecture for validation. So for training, starting from images, and this is an example using iRoads for driverless cars. So this is what front window of a car actually, how it looks like, or what we can see. And we need to determine the type of the road. So we extract features, then we determine the density, then we calculate this empirical probability, if you want, which we call it typicality. Then prototypes, and there may be several layers of prototypes. We call them mega clouds, if you want, if they are aggregated again. Sorry, I went back. And for validation, the architecture is different. Then we have a new unlabeled image, and we need to determine to which type of environment is more similar or closer. So we do this extracting the features and then determining the similarity using the same Cauchy expression that I already shown. And this gives a value between 0 and 1 of similarity or closeness. And we have different values. We take the winner take all. So in this case, it's much more the bottom, the blue class, and we declare the winning class. So this is how it works. We started with different examples. For example, the first application was MNIST, something everybody probably starts as exercise. And we not only determined the accuracy and so on, but also we extracted rules. Sorry. As I mentioned already, symbolic aspect, we extracted logical rules which are clearly understandable for a human. If an image looks like this, or like this, or like this, and so on, then it's 0, and so on. And these images with which we compare, we call prototypes, and they're part of the training data, but a very small part of them, let's say around usually 1 to maximum 10% of the data. And they are selected in a specific way, which I don't have much time to describe, but it's essentially unsupervised learning. And we have set of sorry, such prototypes which form a rule base, if you want, which is clearly understandable. But the mechanism behind is based on winner take all. So we determine the density, and here actually by mu we denote it's like membership, so actually it should be D density to each of the prototypes, or similarity to each of the prototypes, and lambda is the winner per class, and the total winner is declared at the end. So in the first example, we have 10 digits and only 6 prototypes are shown, but in fact, their number may be larger. It's not necessarily the same number for each digit. As you have seen here, there may be a different number. Here we actually only show 6 as well. But in reality, there are different number of prototypes for each class because we train them individually. And in this case, the winner, the most similar, is this pattern, which means it's number 4. And if you look, the second closest is 9, which is quite logical because this is probably the second most closest pattern. And for the second example, the winner is 7, sorry. But the second most closer is 4, which also makes sense. So it's either 7 or 4, but it's clearly it's 7 because it's a big difference here. In some more difficult cases, we also may use top 2 and so on, as you know. So in this case, we achieved 99.55% accuracy, which is comparable or better than any published. And the only errors are shown here, which are very clear that they're not easily classifiable even by a human. For example, this and this. But more interestingly, it's not just the accuracy. We achieved this result for training less than 2 minutes and without using GPU, 2 minutes per digit, so 20 minutes in total, and without using elastic distortion. While these two approaches are by Jürgen Schmidt-Huber's group, so they're very famous, let's say, some of the best results they achieved, but they used 2 GPUs, they trained 14 hours, not 1, but 35 deep networks and so on. So they're not truly even really fully comparable. But MNIST is relatively easy problem and considered almost as a toy nowadays. We moved to face recognition and we used ORL, Oxford Research Lab examples, where there are 40 people, 10 images from each faces, and the task is to use only 1 from each person to train and to recognize the other 9, and then to use 2 and to recognize the remaining 8, and so forth, up to 5. So we managed to do this, surpassing the accuracy of alternative deep networks and other approaches, as it's shown in the table, achieving 90% accuracy when we use only a single image, and 100 when we use 5 images of the same person to recognize the other 5, so no errors. And more importantly, we extracted a rule-based symbolic representation, which is quite logical, like the humans would understand it. In fact, we used not the whole image, but we used segments, which we slided, so sliding segments. And therefore, the rule is actually even more informative. So at the end of the day, the rule looks like this. If the person, for example, if you look at 11, if the person has a eyebrow like this, and eye like this, and hair around the ear like this, and so on, and beard here, then it's subject 11, and so on. It's quite similar to the way a human would describe this image to somebody else. So we extract actually this insight information. We don't have millions of weights. In fact, we have parameters which are only extracted from the data, like mean and standard deviation, which are not user-defined, arbitrary or abstract parameters. Then we move to remote sensing. This is Singapore database, which probably is well known to everyone. And we, again, extracted rules and achieved accuracy. Here it's reported 93, 94%, but in fact, we have examples where we have 97 and above. And I'm not sure if I included them, I will see, but we compared with other pack of words and visual words and other deep networks as well, approaches. Yeah, when we used different ensemble of different segmentations, level of segmentations, we achieved a much better result. So there are extensions of what we did. And then we got, here it's 90, just like above 94%, but we have in other publications 97, I believe. So these were results on remote sensing, and then we moved to some benchmark problems. For example, first we considered iRoads, which is a benchmark for driverless cars, and we achieved excellent result, not just 99.59% accuracy, which is slightly better than using other deep networks, but also the time for training was very fast, and we have only 27 parameters, which are not abstract. They're what describes the prototypes, position in the data space of the prototypes, the mean and standard deviation. If you remember the curve, this is where is the peak and the spread of the Gaussian. So essentially, they are quite meaningful, 27 parameters and very small number. So they can be easily explained. And then we move to another benchmark test called Caltech 256. It's a challenging data set, with 257 classes, and we achieved better accuracy than the reported methods, including SVM and deep learning. It's published, so in fact, by the time of publication, it was a world record. There was no better result published. Similarly, we have a result that is better than anything published for Caltech 101, where there are 102 classes using our deep machine reasoning approach, which is a version of xDNN, combining with decision trees essentially. And again, we surpassed all the published results. Similarly for the faces dataset, and DMR for Caltech 256 actually got even better result than xDNN itself. Right? So finally, to Earth observation, as I mentioned, we are just starting this project a month or two ago, and I give here credit to the PhD student and the other researchers involved, and I'll briefly describe the problem, the data pre-processing method, and just preliminary results. So probably it's a well-known problem of foot detection, because foot is important and affects many areas around the world and causes huge damage. The problem we want to solve is to map the footing extent. More specifically, we want to classify fooded and not fooded areas from images, but not just visual images. As you know, spectral, hyperspectral data have other dimensionalities in addition to the RGB, for example. Food identification can significantly help disaster management, as it's known, and which includes plan relief efforts. And therefore, it's important not only to assess the damaged areas, but also, if possible, to predict and to evaluate this. So part of our tasks will be prognostics and prediction. We started with medieval 2019 competition dataset, which is published. Now we move to world data, but I'm not presenting results for this, so I'm presenting results for medieval. These are 12 bands of data derived from Sentinel satellite by ESA, and the images are with dimensionalities 256 by 256 and 512 by 512. So we used approximately 2,000 images in total, where slightly more did not have foot and 823 had fooding. And this is how they look, the foot true and foot false. And what we did is we performed segmentation using SLIC, and then we derived a much larger number of actually segments, and then we use this for training. So this is how this looks like, and we resize the images, and at the beginning we start with RGB only. As I mentioned, we plan to move to using other bands as well. And we used water index only for labeling purposes. And we developed an xDNN, or explainable deep neural network, the way of the form that I just described, which aims to predict flooding, but also to give some insight why we think it is flooding. So we used for feature extractor a pre-trained on ImageNet on data which are not flooding. There are other data, VGG network, just to extract the features, and we fine-tuned on flooding data later on. So these are the segmented data from one of the images, and the xDNN essentially is an explainable deep neural network which is using prototypes, and I'll show the training architecture, which probably will be more clear. So this is similar to what I presented earlier. We feed different data. We train per class, in this case, 2 classes. Later, we'll be using more classes like land, river, and clouds, and so on. We have such work, but I didn't include these results. Then the first step is to extract features. Essentially, we convert each image into a code of in our case 4096, but it may be another dimensionality vector, 124 or so. Then using this vector descriptor, which is the feature vector, we calculate the density the way I described, and then we calculate the conditional probability the way I described, and then we determine prototypes, which in this case turned out to be a very small number, which is very good. So it's very clearly explainable. And validation architecture probably shows this. So when we get a new image for which we did not have any information, so it's not part of the training, and we don't know whether there is FOT or no, the first step is to extract features, then to compare with the prototypes of flooded and no flooded areas, which are different areas, not the same, to calculate the similarity and to declare the winner. And our preliminary results show around 87 to 80, you can see to 91, depends in which category of accuracy we are looking for. Recall, for example, is 86, which is important. In fact, we have better results, 92, 94, I think, %. But when we deal with clouds, when we deal with some other details, which I'm not presenting at the moment, so this is just to give you an idea. But the proof of concept, these xDNN networks can be applied, and in addition to the accuracy results, they can give you a similarity level to each one of the prototypes. In addition, the number of prototypes is very small. It's in an order of single digit or around 10 maximum per class prototypes images. Well, we started with several thousand of images in total. So we get a very small number of prototypes in each category. We have a digit exact number of estimation of similarity to each one of them, and we make our decision based on this similarity. So in addition to accuracy, we get some insight why we think there will be flood, because it's similar to another situation. Or roughly speaking, when there was a flood in Germany, you compare how it looks like with other prototypes. It may be from the same area, from previous flooding, which is not exactly the same, but it may be even from another area. But parameters of when there is flooding will be more similar to this situation. So this is how it works. It gives you much more insight than a traditional deep network. In addition, it's also computationally much leaner or easier to train, to retrain, to add new images, new situations. Also, it can run without GPUs on a different type of hardware, and therefore it's much more suitable for applications on satellites and so on. So it has a number of other advantages. It's not just the accuracy and not just the interpretability. There are a number of other aspects. But as I mentioned at the beginning in this talk, I just wanted for the short time to give you a perspective of our center. Generally, the approach to interpretable or explainable deep learning, if you want, and some applications including to Earth observation and remote sensing. And this is what I did. And as I mentioned, there are a number of advantages apart, or number of characteristics that are important to look at, apart from accuracy, which usually is the leading, the same like in life, profit is usually the leading. But there are other things we need to pay attention to. It's not just even interpretability, explainability, but also time, energy, therefore computationally lean, very fast is important, parallelizable, parallelization is important, non-iterative, non-parametric. These are important characteristics. Ability to learn from other samples, also collaborative aspects like for federated learning and number of other aspects as well are important. So on this, I'll finish my talk. Just I'll give some details about publication. So this is the book I mentioned. There is another important book, Autonomous Learning Systems. This first paper is important where you can find more details towards explainable deep neural networks. It has already more than 40 citations for less than 1 year, and several other publications which give more detail to the theoretical aspects of the talk. Thank you very much for your attention.
Thank you very much for these interesting insights. We are a bit short on time, but we do have a couple of minutes for questions. So If you want to ask a question, please just unmute yourself, ask your question, or if you're really shy, you can also type them in the chat. So yes, what questions does everyone have?
If nobody dares ask a question, then maybe I start, Anna and Plamen. So as far as I understand, the trick more or less is to restrict the density functions to this set of Cauchy distributions. And this is a kind of regularization of the whole process. So instead of having 200 million of parameters, now you have only 27, for example.
I would say no, not quite. I mean, the main trick, I think, is the switch to prototype-based models. So the first concept, I mean, generally in modeling, you have several different types of prototype-based modeling is not new, but most of the traditional deep networks nowadays, they're of a different type, where you have like a polynomial, if you want, or highly parametric model that you tune. But this is not the only concept in modeling. Like KNN or RBF networks are very simple examples of something similar to what I do, or case-based reasoning. So this is the key, rather than the whether it's Cauchy or Gaussian and so on. Cauchy actually helps later to recursively update it, but the main conceptual shift is to choose prototype versus parametric.
I understand. So you're playing back. So you're interpreting the peaks of the distribution, and you're projecting this back into the image domain, and to say this is.
Yes, I would say it's
this
like
peak corresponds to this type of image. This is.
Yeah, I would say this is a deep version of RBF, but with number of other features. Because RBF is just one hidden layer. Here you have several hidden layers. Also, yeah, not only the Cauchy, but number of other things are different, but probably the closest is RBF.
And the prototypes, they are artificial, so to say, computed images, or are they members of the training sets?
Oh, no, you can have actually both, but for interpretability, these are real images which are closer to the peak.
Okay,
so
I can understand. So you're choosing the one that is closest to the peak.
Yeah.
To each peak. Okay, this is
because there are a few stages which I saved. So once you get the peaks, like in this example, you need to approximate locally as well, or also you need to choose the prototype, and you can either choose the exact or you can calculate it.
And for the similarity measure, you take then the distribution. And is this built in how is it technically done? Is it built into the activation function, or?
No, the similarity is based on this density, while the PDF, the distribution, is actually a weighted form of the density. So similarity is just the density, and it's recursively updatable. It just depends on the data in the feature space. We also use like softmax and the winner take all for the decision as well. In fact, another not trick, but the reason to explain why it's so much computationally cheaper or leaner, we don't use backpropagation for training. So we can use local optimization. So the problem of finding the structure is actually converted to unsupervised clustering, if you want, per class. So essentially per class in the data space, you try to group the data so that you have these local peaks. And this has an explanation, because if you have a highly parametric function, you need to train a lot to try to fit this to the data, because you choose the type of function, like in this case, Gaussian green or the black one, and then you try to fit to the data. Well, so it's from the assumption towards the data approach. While we start from the data, we just aggregate them and we look where the local prototypes are. So it's bottom-up approach versus the traditional in deep learning top-to-bottom approach. Therefore, they need much more time to train and to minimize error to get closer to the true data distribution, while we start from the actual data and we build up.
But when you say clustering, then you mean building up and finding this distribution.
Yes.
You don't mean a separate clustering step.
No. It's like a clustering.
Okay, yeah. So it's a synonym for finding the distribution. Okay.
Yeah, it's local as well. I have in my paper, so essentially I combine ranking with the traditional in clustering. In most approaches, they use distance and forms of distance metrics. Here we use both distance and ranking. So essentially you rank order based on the density distribution, and then you look at both the distance from the first to the second and so on.
Yeah, the results are really breathtaking, actually. I wonder what happens. I mean, in these examples, you showed a data-rich example, so that the number of data points per dimension is very high.
Yeah,
but in reality,
we
of
have
course,
this
the feature space is empty in usually.
Exactly. Because we are going bottom up. In fact, we have published not only the results, and some of them that I said we have better than anything else, but we published also the code. So the code is also on GitHub, xDNN in the its native form if you want. So one can slightly improve for each application, maybe slightly tune it, but you can run it with any other data. And we have very impressive results. I didn't include it here for COVID nowadays. And we're applying to other applications as well. Our application to COVID actually has 200 citations for 1 year, which is more than the original xDNN paper, which is generic. But the code is there. You can try to run with other data sets.
Okay, great. Thank you.
More questions?
I did not include the web link for the code, but probably you can find it on my website, or I can send it later. It's on GitHub.
So we have almost 50 participants. I can't imagine that there is no question. Either you have explained it so perfectly that only I was the one who had detailed questions, or people want to wait until they try out your software and then ask you questions, then come back to you.
I have a question more from the application side. So you showed a couple of applications there, which were all more or less in the image domain. I was wondering if you had thought about applying the approach to other domains. Like I'm particularly interested in text data, but.
Yes. Okay, to text, frankly, we didn't. I mean, this is a work over 3 years or so of a couple of PhD students. I have colleagues who work in NLP, but this was not applied to NLP. The key, I would imagine, will be the feature extraction. But we did apply to data which are not image. In the project with Ford, I didn't demonstrate here, but there is a paper. Let me see if it's listed. The data were relatively simple. On a motorway, you have 8 cars, 1 car, ego car surrounded by others. And the features are velocity, a relative velocity, distance to the other cars, and based on this, to determine the action, to overtake, to keep the lane, or so on. So we have this. If there is time, I can try to find it, but I don't see it here actually, but it's on my website. So we did apply to relatively simple direct problems, not image processing, like velocity, distance. I think there are 20 so-called affordance indicators. They call them affordance indicators. 20, so vector of 20. Here it's 4096. But we did not apply to NLP. But I would imagine it will work. The only problem will be the feature extraction, either word to vector or keywords or something else, which in NLP they do use. Also, maybe cosine similarity will be more appropriate than Cauchy, so one need to research a little bit. But the concept will be, again, you have prototypes for certain situations, so the concept should work, but there will be a need for some changes. Probably.
Yeah, I imagine that would be really interesting, because interpretability is sort of under-researched in NLP. So
the nutshell of the innovation is that to use prototypes, which itself is not new. I mean, of course, it exists. Tip Shirani published around 2012, a nice paper, and everybody knows that, for example, KNN works excellently, even if it's not even a proper machine learning method. Other methods are also known, like RBF, as I mentioned, but they are not deep learning, and KNN is not, as I mentioned, machine learning, and you need all the data. Well, here the number of prototypes is usually a small subset of the data, so it's not the same. But this is the concept. So this is the conceptual difference. And at the same time, you still have the deep learning architecture, number of layers, and many other elements. And also you can have the symbolic representation in the form of row basis. So if you keep this, you may change few things. You may need to change few things like exact similarity distance or feature extractor, I would guess would need change. Maybe something else as well. But this concept can be expanded.
Thank you.
I was wondering, and sorry if the question is naive, I'm not a technical person. I was wondering, how do you select the prototypes from the data set? And how do you then prevent bias when you're selecting the prototype from the data set?
Thank you very much. This is a very good question, because this is actually the key, not technical difficulty, but let's say the key concept I mentioned, the prototypes, but the key step, if you want, because feature extraction is time consuming and so on, but it's more or less established in each area, in image processing separate. So this is one of the key, not original, but different to the others. So I mentioned very briefly, and here there is a visualization, but essentially when the data come in, so there are two versions. We have this, we call it ADP. One of the papers is on this approach. It's autonomous data partitioning, essentially, we call it. It's like clustering. And one is online or evolving approach, the other is offline. In offline approach, you have all the data and you need to find these prototypes. In the online, you have data coming like stream. So you compare for each data point, you do calculate the density in the form of this Cauchy function, which I mentioned, and then you compare these densities. So essentially, in simple terms, locally, the winner is the point with the highest value of this density, because it describes too many points, and it reduces to a local minimization problem, if you want. And in simple terms, if you have online, you can just, when the point comes, if the next one has higher density, you just replace the previous with this one, and so on. It's simple, because there will be other points not locally, and therefore I mentioned ranking as well as this are combined. So this is described in the paper, but I try to now very briefly describe the concept. So essentially, each point has a maximum locally value of D, of the density. So it's in mathematics, there is, in system identification, mathematical modeling, there is a problem called multimodal systems to identify the modes, mode identification, MOD, mode identification. So essentially, this is a problem of mode identifications. And you can solve it either offline, and then you can have even iterative processes or so on, or you can solve it online. So we do it online. These are local maxima.
Thank you.
I also have one question related to the application point of view. So in the examples with the images, you showed like in the architecture processing for a single image. So my question is, would the architecture need to be changed if, for example, we have a time series of images as an input?
Okay, thank you. Yeah, so if it's a video stream.
Yes, for example.
Okay, so I don't think we tried video stream, but I think it will stay the same. You have prototypes, and even in video stream, the images are actually coming with some frequency. They're not continuous, they're discrete, let's say 24 per second or whatever. So you can process them one by one. But if you want to keep the information of similarity of consecutive images, then maybe you need to build the set of prototypes in a different way. We haven't done this, so it's a very interesting problem. Or otherwise, if you are just looking whether there is a car anywhere, probably you can keep the same architecture. But if you are looking for a type of motion of the car or something which actually is described not by a single image, by a sequence of images, then you may need to organize the prototypes different. And maybe set of prototypes will not be the red one here, cars, but it will be one type of motion of car, another type of motion. So you need to expand this concept if you want to apply it, not straight away, but there will be a modification if you want.
Okay, thank you.
Okay, any more questions? Otherwise, I think we can stop here. We're a bit over time. Everyone, thank you very much for joining us today. In particular, Professor Angelov, thank you for your interesting talk and for the responses to our questions. And yeah, I hope to see you all at our next talk.
Thank you very much for the opportunity, and I hope it will be a kind of a beginning of collaboration. Obviously, I'll return the gesture to invite Professor Zhu, but I'll be happy if anyone from you is interested to collaborate. I'm happy to respond. As I mentioned, GitHub address I'll send later, and if there is anything else, I'll be happy to respond. Thank you very much again.
Thank you.
Thank you. Bye-bye.